Alright, so in the last video we evaluated a triple integral where we were given the bounds on each of the integrals. Here I want to evaluate a triple integral where I'm given the definition of my region Q, but I need to come up with those bounds myself. Okay, so here we're looking at the triple integral over Q of 2x dv, where Q is the region under the plane 2x plus 3y plus z equals 6 that lies in the first octant. Okay, so we've been sketching planes a lot recently, so let's first thing to do is get a little sketch. So this is going to hit the z-axis at 6, it's going to hit the x-axis at 3, and the y-axis at 2. So Q is the solid here, bounded by the plane 2x plus 3y plus 6. Oh my goodness, 2x plus 3y plus z equals 6. And also by each of the coordinate planes, right? The xy plane, the xz plane, and the yz plane. All right, so when you think about what we're doing here to evaluate the volume, we're taking little pieces, say, little pieces of the volume inside the rectangle. Inside the pyramid shape, I guess let's call it. All right, so I'm taking pieces like this. So the first thing I want to think about is what the bounds on Z are, right? So as I move along, and I'm taking these these should be 3D, but these 3D pieces, what happens to my Z values? Well, they come and hit the top of this plane, right? So Z ranges from 0 to the top of the plane, which if I rearrange this equation is 6 minus 2x minus 3y. Okay, so now we want to focus in down here in the xy plane to look at the bounds on x and y. So I'm going to resketch that below just so I have it here. So it hit the x-axis at 3 and the y-axis at 2. So we're looking at that shaded region. And now this is the same setup as we had with the double integrals. So I can take a vertically simple region, or I can treat it as a horizontally simple region. I think what I'd like to do is vertically simple. So first I want to think about, as I move vertically along here, what my bounds on y are. Well, they go from 0 to this line. So what's the equation of this line? Well, this is the plane when z equals 0. So this is 2x plus 3y equals 6. And rearranging, that's y equals, let's see, negative 2/3 x plus 2. Okay, so my bounds on y are, y goes from 0 to negative 2/3 x plus 2. And now finally, think about what's happening to x as I move along here. X goes from 0 here to 3. Okay, now once I've got those bounds, it's just a matter of setting up my integral. So I'm going to have the integral that's going to go dz, dy, dx. Let's just set up the triple. And I have 2x. I can scooch that in a little bit. Okay. All right, so bounds on z were from 0 to 6 minus 2x minus 3y. Bounds on y were 0 to negative 2/3 x plus 2. And on x, we went from 0 to 2. 0 to 3, my goodness. There we go. All right, once I've got it set up, it's just a matter of evaluating that integral. And my advice to you is just to take it one step at a time. These integrals shouldn't be terribly complicated, but they are tedious. All right, so the first thing I want to do is integrate with respect to z inside here. Okay, so there is no z in this term, so this integrates as, let's leave the outside integrals. I really want to make that 3 to 2. There we go. From 0 to negative 2/3 x plus 2 of 2xz from 0 to 6 minus 2x minus 3y dy dx. This is the integral from 0 to 3 of the integral from 0 to negative 2/3 x plus 2 of 2x times the quantity 6 minus 2x minus 3y minus 0, right? Dy dx. So that's the integral from 0 to 3 of, let's just clean this up one more time, negative 2/3 x plus 2 up here. If I distribute, I'm going to get 12x minus 4x squared minus 6xy dy dx. And now I want to integrate this inside integral with respect to y. So I'm going to leave the 0 to 3 integral on the outside. When I integrate 12x with respect to y, I get 12xy, then minus 4x squared y minus 3xy squared, evaluated from 0 to negative 2/3 x plus 2 dx. All right, so let's plug in. We're plugging in for y. So I get 12x times negative 2/3 x plus 2 minus 4x squared times negative 2/3 x plus 2 minus 3x times negative 2/3 x plus 2 quantity squared dx. Now I know you don't want to watch me clean this up. This is just cleaning up a polynomial. So let me just tell you what we get when we distribute and FOIL out that last term. You should get 4/3 x cubed minus 8x squared plus 12x dx. And now this is a Calc 1 integral. We're just integrating a regular polynomial. So again, let me just tell you what you get. The answer should be 9. All right, I also want to look at a couple more examples just setting up these integrals. So let me turn the page and let's look at some of these. This is example 4 in the book, so if you'd rather just look at it in the book, that's fine. Let's set up integrals. For the volume of each solid region. Okay, so remember, volume is going to be the triple integral over Q dV. All right, so the first example we want to look at is the region in the first quadrant, first octant, sorry. Bounded above by the cylinder z equals 1 minus y squared, and lying between the vertical planes, x plus y equals 1 and x plus y equals 3. Okay, so the first thing we want to try to do is get a visual of what's happening here. All right, so z equals 1 minus y squared is, oops, I wrote y up here, didn't I? There we go. Is this parabola, and I'm going to just draw in the first octant, right? So it's this parabola, z equals 1 minus y squared, that's been stretched out over the x-axis here. All right, and then we want to bound it by the planes x plus y equals 1 and x plus y equals 3. All right, so x plus y equals 1 is going to, let's say here's x equals 1. It's going to be crossing something like this. And then x plus y equals 3. So here's 3. And it's going to have the same slope, something like this. Okay, so this is a terrible picture. You should just look at the picture in the book, but this is sort of the idea of what this looks like. Let me try to clean this up a little bit. So say here's my plane, x plus y equals 3. Cutting that off. All right, so let's think about how we're going to integrate. So again, when I think about taking pieces here, I first want to think about what the z bound is going to be, because I'm going to take pieces going this way, hitting up onto this curve. So z is going to go from down here in the xy plane up to this surface up top. So my bounds on z are 0 to 1 minus y squared. All right, now let's look down here at what's happening in the xy plane. So let's focus in a little bit. I want to sketch the line y equals 1 minus x. So that's going to cross, I've drawn this sort of poorly, 1. So here's 1, here's 1, 2, 3. Okay, so here is y equals 1 minus x, and this is y equals 3 minus x, so that's going to cross at y equals 3, comma 0, and when x is 3. And now the region that we want stops when y is 1. So we're going to stop here. And that's because it's coming out from that curve here, right? So this crossed at y equaled 1. That's where it hits the xy plane. All right, so here's our region. I've got y equals 1 minus x here, y equals 3 minus x here. Now I want to decide next if I want to take vertically simple or horizontally simple. Well, in this case, actually, if I do vertically simple, here I'm running from the line to y equals 1. But once I cross x equals 1, I'm running from y equals 0 to the y equals 1 for a little bit. And then again, when I hit here, I'm going to switch to y equals 0 to this line. So I'm going to have to break this into multiple pieces to deal with it vertically simple. So it's best if we go horizontally simple. So I'm going to go this way. So I want to rewrite these equations in terms of x. So this is the same as x equals 1 minus y and x equals 3 minus y. All right, so my bounds on x then become x is between 1 minus y and 3 minus y. And now finally I want to think about my bounds on y. Y's, if I take these as horizontally simple slices, I'm going from y equals 0 up to y equals 1. So 1 to 0. Sorry, 0 to 1. Okay, and thank goodness we're only asked to set this up. Okay, so what is the volume? It's the triple integral from 0 to 1 of the integral from 1 minus y to 3 minus y of the integral from 0 to 1 minus y squared. And what is my order of integration? I want dz, dx, dy. And there we have it. All right, I'm going to pause here and maybe we'll come back and do some more examples.